thing today is to work on the ways to do products in algebra or group theory. So this is the nitty-gritty. If you can't find good ways to do products of group elements of some symmetry group you're working with, you need to back off and find a good way to get those products, because that is what makes group theory work, or algebraic, ring theory, whatever you want to call it. And we've been dealing with both groups and an elementary algebra that involves the Jordan-Pauli U2 spinners. Those operators make a little multiplication table. So that's the subject today. The subject is to see how to do that in various ways, ranging from the algebraic, which we've sort of already done a good part of that, and we'll just carry it to its completion as far as finding a general product of a rotation operator of a particular set of axis angles, a particular set of the Darboux angles. And of course, converting that to Euler angles is something we've already done, but the products, we really haven't gone all the way through that yet. And then I want to see some geometry associated with those products. And part of the reason for doing that is I have an analog computer that does this very complicated algebraic problem and some others. And for a while we sold this device, which is on the screen over here, sitting on the overhead projector, and we'll actually do a typical product on the slide reel just to see how that works. But that's getting a little ahead of us, because the thing that we need to discuss first is Hamilton's idea of drawing arcs on a sphere that's exactly half the angle that you want to rotate. And once again, that number 2 or a half springs up in a very powerful way there. So let's begin just with the discussion of the operator on operator products, the things that we've already done, but I want to get it into algebraic notation. Remember, we had two kinds of generating matrices. It's the name that's given because it generates the things we really need, which are the irreducible representations of the group. But the sigma matrices that are back in class 4, and this is a link that you can go back real quick and look at this question. The thing we didn't show there was the algebraic expression for both Hamilton's quaternions, which are just I times Pauli-Jordan's spinner operators, so that I comes in to take away the I from the actual product expression for the stuff that most people know about. This is what you find in a textbook in advanced quantum mechanics. And then this is an expression that Hamilton would write if he did write tensor equations for his quaternions. And the difference is pretty much the minus sign here and no I here, whereas for the sigma is delta function is just there. These things square up to +1. These things square up to -1. And then the epsilon symbol, the permutation symbol, Levi-Civita thing, it's mostly 0. It's only 1 when all those indices are different. And we've went through the products basically one by one, but this is a way to express it in a single line, which is something a mathematician relishes. So that's what we're dealing with here. The quaternion multiplication table is here. The Pauli sigma multiplication table is here. So these are just the write-out of these two equations. Now, the commutation rules, which we will be interested in for our Engel-Amenov work, the product of something you knew and then the reverse subtracted, that is pretty easy to see from this thing. This term will cancel out and leave me with 2 times I and then the epsilon tensor there. So that is a pretty easy thing to see. Now, what you remember is that what we wanted to work with for our angular momentum in a 3-dimensional setting was something that was 1/2 of the appellate. So we have the Stokes or spin vector mu as a half of the sigma for each of the 3 components, A, B, and C, or X, Y, and Z, and then there's the 0 or 4th component. We always use 0 for that one. And then this just stands for Jordan here, this stands for Stokes. As far as I'm concerned, if we're going to put inventors' names on our variables, then that's the way it would go. But in this case, by taking that half here, you see, it gets rid of the factor of 2 here. So this is the angular momentum commutation relationship that we're going to run into later. Now the next class we're going to do involves harmonic oscillators, and we're going to build those operators out of the harmonic oscillators, and they have really simple commutation relations. So that's all that I need to say about that. Now, what we're going to do now is actually go through the algebra of taking a full rotation operator, and remember that's an operator that's been made using the crazy thing form, and get a closed form formula for that product. Okay, and again, this link goes back to some of the things that you need to do that, which I will mention here. But the important point that I want to make, and let's put all of this on the same screen here, the important point I want to make about the exponential form, that is the crazy thing theorem, is we're not just taking an exponential and then adding the exponents. You can't do that when the operators don't commute. So it would work if these 2 vectors were along each other. Then it would be a sum of the angles associated with their rotations. But when they're not in the same direction, then you have some work to do. And so it's necessary then to make use of the crazy thing theorem, if you recall. This takes you back. I actually haven't tried those links yet, but if you do and there's a great big cloud of smoke comes up, I'll know what happened. The crazy thing theorem is sometimes dangerous for other reasons, but the main reason is that all the things in it that involve these factors do not commute. So A here comes second, this one comes first. Remember, if we're going to work on kets, that's the way you read it. This operator is going to act first. This A operator is going to operate second. Okay, and that's just our convention now, since we always work on kets. If you're working on bras, then it's the other way around. Then A goes to go first, like it does in the alphabet. So this is what we're after. Is that we want to expand this entire thing out and put it in this form. And when we do that, we'll be able to equate this quantity here and the 3 quantities that are sitting here and here. So the first step is just go ahead and expand it out. But right away, when you expand it out, it's these 2 making a product that still has to be solved. And this is where the Jordan-Pauli identity that's up there on that screen comes into play. And this again has a link if you forgot what happened during that discussion. But it breaks it down into a cross product and a dot product of the 2 vectors that are serving as components, A and B, of the crank axis vector. This is a unit crank axis vector. Here I'm just using a notation to indicate the full crank vector. So we have to reduce this thing to a form that has a dot product and a cross product. And that's the real trick to this algebra right there. So we end up with three scalar terms. This is a scalar product here of unit vectors and some sines and cosines of the angles that we will actually be rotating A and B at the crank axis. And then all of these things here are vector quantities. This is the A vector for the second rotation, and then this is the B vector for the first rotation, and then there's a cross product vector that involves both of them. And each of the factors involve sines or cosines of the two angles that we're rotating. So that makes pretty good sense, because it is now that we can go ahead and take this vector right here as a unit vector. That is the unit vector that we're talking about. I'll put it here in a minute, but anyway, the thing that multiplies the dot sigma right here will be some sort of product AB, so we're going to define that. And then this thing right here, that's the first step, is to just evaluate this coefficient, because this coefficient right here has to be the cosine of whatever the answer is for the angle that will result from this particular product. So there's the first term in the crazy thing theorem, and then it's this vector term right here, the one that involves the sine as opposed to the cosine, which is just multiplying a unit. The one that involves the sine is multiplying this vector right here. But that vector we have that vector sitting right here. So that's the second step of this evaluation here. I'm going to go ahead and make that one catch up eventually too. But anyway, here's the second step, the coefficient of minus I dot sigma. That's the thing that derives the unit vector that's in there. And it has a sign on it according to crazy thing. So there you are. That is a formula that lets you evaluate any product of whatever the crank vector and length is, whatever this one's crank vector and length is, you can get the answer for the product. The trouble is that it's pretty hard to visualize what that thing has done, and that is what I would like to explore more than just working out this. This is something that is easily programmable. So when it really comes push to shove and you need a lot of products, obviously you need our wonderful silicon devices here, right? Okay. Before the silicon devices actually came,
so Dr. Harter,
there's the polyunity right there.
Did you program this in HTML? Generate all these products in HTML? Is that your platform? This particular calculation, the computation, involving products, did you do it on HTML?
Whenever you need a product, this one will work for...
Yeah, on which platform?
He creates in Keynote. He does it by hand.
Okay.
And then he builds the Keynote, and then we convert that to HTML.
Okay.
That's the master.
Okay.
Yeah, this is, stuff that becomes a PDF on the web.
Yeah, we convert that.
Yeah.
So everybody can get into it.
And presumably all these links to previous stuff work as well, right?
Oh, no, my question was when you have to do actual computation involving many products, so what?
Wait for a slide or two.
For some people, Brad has worked for Mathematica, and he uses Mathematica almost exclusively. One of the things that you would like to have is a program on Mathematica that does this, and I'm sure they're out there. It's just a question of whether they've been put in the right form and whether they're using A10-2 in the right way. You can get phase errors that are pretty embarrassing if you're not careful. So it's not a trivial thing. This is sort of summing it up right here. First step, second step.
So this slide
the idea is you have to get this first in order to evaluate this thing, right? Yeah. You gotta get this angle, okay? Then you can do the vector stuff, okay? Pretty easily, because it requires the angle too, right? The input angle.
as well.
Become more clear. He's
So
going to bring this into the discussion.
this kind of sums it up right here. There's the angle. It's the arc cosine of that. Now you have to be careful when you get to arc cosine so that it gets you, so you know what quadrant you are if we're talking about complex radius, but if you're not, you're in pretty good shape with this. And then there's the vector that goes with it right there, and it involves dividing by the sine of that angle. And of course that goes to infinity if the rotation is null. So you have to watch out for that. It might be that you didn't know that those two were inverses of each other. You know, it's pretty easy to tell, but you should have to worry about that. Okay, now what's the geometry of this? And in particular, what's the geometry of the other kinds of products that you can make? This is the binary product. There's a transformation product where you do A, B, A inverse, for example. We're going to talk about that. That's where we talk about equivalence transformation, okay? Now the equivalence transformation is not that difficult for most of our rotations because this is just telling us, well, just do a rotation on that darn crank factor and go to work, right? It's going to be the same angle of rotation. It's just going to be in a different direction. So I didn't put that up here, but that I think that'll become obvious. That's what the geometry is all about. So once you realize that, that becomes easy. But the thing that we've already done algebraically was, like a whole screen full of stuff that involves sines, arcsines, and arctangents, and so forth. This conversion between the coordinates alpha, beta, and gamma, and the group parameters phi italic, theta italic, and crank angle, that is also cumbersome algebra. So having a way to do that easily was a goal of mine for a long time. And so that's what we want to do here. And then also we're going to be getting into subgroups of all these big groups that we're talking about here. Right now we're just talking about rotation 3 and orthogonal 3 dimensions. But there are lots of subgroups of those of big continuous Lie groups. So we'll be working with those. Now that's a whole different story here. You're now making tables that aren't too different from the algebra tables for the quaternions or the sigmas. So this is the main part of what I want to talk about today. It's just to get a good feeling for what happens when two group operators get to tango, as it were. It takes two to tango here. And so we need to discuss that. Now the point I'd like to make right from the beginning is the old saying, whenever something tricky is going on a magician's stage, somebody will say, it's all done with mirrors. And sometimes they're right, the famous thing where the elephant suddenly appears and then disappears. All those tricks involve some pretty good optics. And this does too. And it's worth seeing what it is involved. And we've got a couple of mirrors sitting out on the table here at a particular angle. And I've got some pictures that come from the classical mechanics text where we first really got to describe the geometry of mirrors. It's really quite beautiful. And these sigmas that we're working here, whenever you see a sigma in a finite group theory book, it almost always means a mirror plane reflection. So it's not a coincidence that they use the letter sigma. The question is, did Pauli and Jordan know that? It's not clear, but it is certainly the way it's come out. We've had sigma sub A, which is the asymmetric diagonal sigma. That's actually sigma z there, right, by Pauli's notation. And then the bilaterally balanced sigma B, well, that's sigma x. That's Pauli's notation, Jordan's actually. And then we have a sigma c, which is kind of weird, and we're going to get to that at the very end here because it's also a reflection. It's something that squares to 1. All of these sigmas square to 1. You never should forget that. Okay?
Special operator.
So, what do we got here? Now, what's interesting about this is sigma A, very clearly, if I'm going to call this the x-axis and this the y-axis, we didn't do that before because we wanted to reserve x and y and z for the three-dimensional space. We call this one the x1 axis and this the x2 axis, but I thought I'd clean up the notation a little bit just for this mirror section here, where we really are working in x and y space. Well, that's the two-dimensional oscillator orbit space. If you don't plot the momentum as well, you can use real numbers totally in the two space. That's not a complete description of what's going on, but it's a good start. So the basic idea of having a sigma A operator that flips the y to minus y, but leaves the x completely alone, it doesn't change it. The vector's right in the mirror plane, so that dotted thing should really be on top of you. You wouldn't see anything has happened. But this is a major change that's occurred there. So that's the 1 and minus 1 at work on this thing. Now what about sigma B? That's kind of a weird thing. Now you can see pretty well what it's doing there. It's switching x over to y while it switches y over to x. So this one goes and picks y up and brings it up to the top. This one waits and grabs x and brings it down. That's the mirror that's at 45 degrees. Now we kind of saw this when we used the B dynamics. Then the 45-degree line, you see, was one of the eigenvectors. And the other eigenvector, which is not shown here, is at minus 45 degrees. So we kind of already know this from the physics, but it's important to say that this is a geometrical fact to make it clear that it really is. Now here's something that's quite remarkable about the spinners. If you want to make a reflection that does the x-axis instead of the y-axis, you simply drop a minus sign on this thing, right? So now your minus is here and your plus is here. So that's going to change x to minus x, and y is just going to sit there. So this is the mirror reflection through the plane is perpendicular to the x-axis, whereas the one that we started with here was along the x-axis. So it's kind of a twofer. You get two reflections for the price of one. It doesn't cost too much to put a minus sign on it. Okay? Again, the square of that thing is the unit operator. So that's what's really at work here is these alloy spinners. The question is, what about minus sigma B, where I do this in a minus here, right there? How does that play out? Okay? Well, it's a minus 45-degree mirror plane. Plus sigma B is in one we've drawn. This one would be around a plane that's perpendicular. Same story as this. This is perpendicular reflection to this one. So that's kind of cool. Then again, another twofer. Okay. Now, what's interesting also is, if you get tired of just doing x and y axis, you can go ahead and add up these two in any combination you want. And remember, the dynamics that we talked about was a Hamiltonian that made a hyperbola, and all you had to do was take a linear combination of the two, A and B, and that made you some A-B dynamics that had an Eigen's normal mode coordinate. It was at an angle that was something besides 45 or 0 degrees. And so this one will be at some arbitrary angle, phi over 2. If you have a coefficient cosine of phi, then that's where it is actually going to be. Now to check this out, you see, you ask, what would the mirror plane do to, say, the x vector? Okay? Well, if the mirror plane is up there at angle phi over 2, it's going to throw the thing twice as far. The image is going to be just as same distance from the mirror on the other side that this image is on this side. So I'm indicating a little dashed line there from the tip of the initial vector to the final. And that then means that the effect of this operator on x is to give you a cosine of phi on the x component of the result, and a vertical component, sine phi, for the y component, you see. Well, that's kind of neat. I mean, it's just the same parameters as this, so maybe not too surprising. But then the other side of the story, it's a little harder to see this one because it goes so far, but the mirror is going to reflect the y down to here. And that's going to be a sine phi minus cosine phi of y. It's going to have the same component this one does of y is now a component of x, and then the cosine that sits here is going to here, but with a minus sign. So this is a matrix that's worth remembering. Well, it's easy to see it. You just go cosine of phi of this times sine of phi of this, and you get this. It's almost a rotation matrix. The only thing that differs from the rotation matrix is the minus sign now is now sitting on the diagonal. Whereas if you're talking about a right-handed rotation, it would be here, right? So it's almost a rotation. Okay, but it isn't a rotation. We got to make that point very clear in a little bit of playing around here. So let me, before I answer your question, let me get this thing up to speed here. There's where we are. Okay.
Oh yeah, so you could still work out the algebra with imaginary components to sigma A and sigma B, right?
Except then you need to draw in complex space. Except for just doing C by itself. You remember what C did by itself? It didn't have a flat normal mode, right? It had circles, right? C for circle, right? You're out of the plane world, you see, with the third sigma component. But yeah, we like to add them in there too. We can make a Hamiltonian all three, right? And that's when you get the ellipses. Okay, so this right here is just giving the ket notation for all of that. These are the matrix elements written in Dirac notation, just to make this thing fairly clear as far as the algebra goes. Geometry doesn't help much if it isn't helping the algebra, so we have to show that algebra to really do a good job of it. Okay. Now, when you make a product of these two, and that's an interesting thing to do next, is just to say, well, what happens if I do sigma A like this? It's real simple. But then this is a little more complicated. What happens? And you really have to be careful now, because these two sigmas, this one a component off of the A, this one a component off of some vector that isn't there, and that's what we had to do to start to get the crazy thing theorem working for us. If we'd had this going, we would have simulated that reduction. But this mirror sigma phi, this particular operation is now in a situation where it will go second. Remember, this guy first, that guy second, because we're going to be working on kets. If you want to change that, you've got a lot of writing to do, because it would change all the textbooks if you wrote a textbook just for bras, right? Maybe a feminist movement or something like that. You'd do that, and where you'd have both sexes mad at you. Now I put this together, this particular one, and now I get that thing I was talking about with a minus sign up here. That's cool. Okay, that means two reflections give you a rotation. Wow. That is worth celebrating, okay? And the rotation angle is twice the angle phi over 2 between the mirror planes that we're actually dealing with. So here we're getting at, in a very simple, almost grade school geometry, and algebra, and that 2-to-1 business between the vector space and the spinor behavior. Stuff going on in the two-dimensional oscillators is going half as fast as the stuff out there in the ABC or XYZ vector space. Well, we can see kind of why that is. Because I'm starting to make some vectors here, and by George, they're going, the deal here, this angle phi, okay, is twice the angle between the mirrors, which we thought was a telling thing.
Dr. Harter?
Yeah.
So like they usually, like that matrix that you have up there.
This one?
Yeah, that one. They usually.
This one is a reflection matrix.
Uh-huh.
These are both reflection matrices, but the result of doing 2 reflections is to get a rotation.
Okay, but you just answered the question I was gonna ask. Wow, yeah,
Equivalence,
you just
right?
answered the question I was
Yeah.
gonna ask. I was gonna answer like 2 reflections. It's a rotation.
That never makes a reflection, right?
Yeah.
Okay, I'll explain that in just a minute. But the other thing that I think is interesting is you can do this with translations too. And this is what is so amazing about that book by Keim, Goodman, Strauss, and company. Okay? And this is Conway.
Oh yeah, this is.
Conway has no use for translations. In fact, when we gave a talk, I said, okay, now where are the translations? Oh, that's just for physicists. I don't give a crap about translations. Okay, it's all it's in my group, right? And here's how he translates, okay? He wants to translate to this point. He puts a mirror up here, right? And he reflects himself. Now, he dies in the process of doing that when you reflect yourself. If you're really going to become that from a right-handed to a left-handed, there's going to be blood all over the place. You're dead, right? But you imagine that you do it, okay? So then he goes, and here he is over here, now he's left-handed, right? And then you do another reflection, say, we'll put it anywhere, and now you're back to your own self, but you have translated, right? Without changing handedness. Okay? So, I just inverted that book down there. Anyway, the idea is that you can do solid-state physics just with a bunch of mirror planes. And you want to do a translation to you, I put a mirror plane halfway there. And then I put another one. You can work it out so that you translate everything just by reflections. 2 reflections will give you a translation, just as 2 of these guys will make a rotation. In this case, you're thinking of translating an angle when you're doing that. So keep your mirrors parallel if you want to do translations. Put it slightest angle there, whatever that angle is, you're going to do double that. Okay, so that to me that's really quite interesting. It means that really we should be doing solid-state physics differently if we want to follow the mathematicians.
Reflected planes out the wazoo.
Yeah.
Like just the 2D.
But there's got to be a way to manage that. Because you already know the answer, right? The translation vectors add, it's an abelian addition, right? And every translation is 2 reflections. Okay, but you can also talk about the reflections in Singularity, which you couldn't do before. Okay? Okay. So, the sigma A and the sigma phi have been put in that order. Sigma A is first, sigma phi is, let's do it the backwards, let's do phi first and A second. And same geometry, same sort of playing around. And lo and behold, they're not equal. We knew they weren't going to commute, but look at the rotation that we get now. It's just a rotation the other way. So I think that's, pretty cool that you can get both rotations. So if you do this translation first and then this one, you get something that's there. The other one will put you negatively. This is a nice rotation right-handed. This is a nice rotation left-handed by same angle phi, which is double the angle between the mirrors. Okay, so that I really want to make clear. Now here's your C you were asking me about, where the Bella you were asking about, where that guy comes in. Okay, I do sigma A times sigma B.
That's right.
I get this crazy thing.
Yeah.
Okay, but then I just say, hey, that's nothing but good old C, right?
Yeah.
So I take the I out. So there's your multiplication rule. Sigma A, sigma B equal I sigma C. That's the table we started with the day that we did the very first class. So this is an XY rotation by minus 90, but you can think of it as an imaginary reflection if you want. Now, does that get you anywhere physically? I don't know yet, but certainly it gets you somewhere if you realize that this is making circles in the Hamiltonian model, right? I turn that C on, I got chirality, I got Coriolis, I got all the things that begin with C. Circle being the most important of them, since that's what you'll be getting in circular polarization. And then you start adding that with this, and you get the elliptical polarization, which is what all polarization is. The other linear polarization is a set of measures zero.
Sometimes referred to as a null.
As a what?
Null, N-U-L-L.
Well, null chirality if it could get right on it, right? But you can never get rid of it. It's always in there, right? Especially when you're doing the quantum, which is what we're going to do next, and that means the ground state 0 point motion is always going to be going, right? So can't get rid of it. Can't get rid of it.
When we say XY rotation by minus 90 degrees, basically it's a rotation about the z-axis, right?
The thing that comes out of this plane here.
See, so it's
Yeah.
a rotation about z-axis
And
by
so
90
is,
degrees minus
so is
90.
this.
Yeah, sure.
Yeah, so is this.
So the rotated vector lies in the XY plane, and it's a rotation about z-axis.
But this is not any space. This is a spin
Well, I'm
space,
just
right?
using XYZ.
Well, when we use these for a physical thing, yeah, it's part of the phase.
What about the like?
The circular, of course, shows its phase by where it is, right? Whereas the linear, it's a little harder to see the phase because it's just going back and forth over the same track, right? It's a little harder to see the phase. So what you do is you make a phaser, right? You have a real and imaginary part, and that's, of course, what all our geometry of wave functions is about. That's why we do phasers. So we're prepared for anything that can offer as real or imaginary. Yeah, that's the trouble with quantum mechanics now, is that all the textbooks, it's all dead stuff in terms of chirality. They just draw a wave function. They don't draw it having its heartbeat of 10 to the 24th hertz if it's an electron. So, it's kind of neat. All right, now, I'd like to feature the famous clothing store mirror. That's the picture that you see up there. We might as well put it up here as well. This guy, okay, and that is the actual mirror that made this drawing. And I just took a picture of the cell phone, and you can see that this particular thing that's set with a angle. This is one mirror right here, and this is the other mirror right here. Here's the sketch of it. Okay, so we're talking about a phi over 2 angle of 60 degrees. That means the actual rotation this thing is doing is twice that in the space we're living in. So the object that you're looking at has been rotated. If this is the right hand image, the thing was rotated by plus 120. If you look at the image over here, it will be rotated the other way, minus 120, from where its original position is. Okay, and you can see that going on there. Now, notice the handedness. This is a right-handed basis here, A, B, right-handed basis. This one's a and it's backwards, right? But then, right, I can read that one. That was right-handed basis. I can see it, right? There's been two reflections to make that. So that's got the rotation of twice to the 60
yeah.
from this one.
Dr. Harter,
Yeah.
could you please once again tell me how the two reflections happen? I just want to see those, visualize those reflections on this.
That's why you should just come in and play with this thing. But the basic idea is you can sort of see it. I've got my left hand there, right?
Right.
And immediately I get an image of it,
That's right.
which is right-handed,
That's right. Yeah.
right? But you see that this is a right-handed basis. This thing right here, just forget the reading, you can't do easily. And notice that what you're looking at here, if this was A, there's B there, okay? But going the wrong way. Then I get it back right again here, and then it's wrong again over here, and then it's right there, and then it's wrong there. That's just the image you see of my, again, my left hand sitting, if I were really there at this point. So this gives you a pretty good feeling of what this sketch has in it. The sketch is pretty obvious, but when you see everything, the whole neighborhood being flipped, it's kind of spooky.
So reflection it's synonymous to parity operation in quantum mechanics, right? Like,
You bet. Yeah.
Can
You just imagine taking an imaginary mirror
yeah.
into an atom with all of its lobes and things, right? And taking every one of those lobes and putting it on the opposite side of the mirror by equal distance.
So which means it's a discrete symmetry in maths.
Well, if you were to take the wave function that you originally had plus the wave function that you're going to get by that reflection, yes. But I like to think of them separately at first, right, as a separate entity, because they both exist perfectly well. It doesn't hurt an atom to undergo a reflection. It certainly doesn't hurt a light wave to undergo a reflection. They love to do it. They come up the mirror and come back reflected. I never heard one of them scream. And we're all made out of that stuff. But when you do it to us, we scream. We're too complicated. Now this is the one that I always mention, that this is a work of art that sits, it used to sit outside the Guggenheim Museum in New York. I've seen it other places too. Big pair of mirrors, really big as this room, extending out to about here from the wall, and then another one going that way. At right angle, we're talking phi over 2, the angle between the mirrors is 90 degrees. Now you know what that's going to do to the rotation, right? It's going to rotate by twice 90. So you see that. Everything here ends up, this particular one right here, that's the image that I would be particularly interested in because I can read it. It's 180 degrees, okay? This guy here, there it is, 180 degrees. Okay. But that's not what you notice when you see this, what I call sidewalk sculpture. Because what the artist has done is he's very carefully silvered the corner, and then he lets the silvering become less and less until the edges just don't reflect at all. So it's just glass. Okay. But when you look at the thing, the first thing you see is yourself. No matter where you are on that, and we can do that with this. If I get that exactly 90 degrees and put it so everybody in the class can see into that 90 degrees, everyone will say that they're the center of attention. Right? So call this the selfish mirror. Right? And this is in a crowded street on New York, right? You know how New York is. It's not as bad as Bombay, but it's pretty bad, right? Especially at rush hour, okay? So there you are in a rush hour crowd, you know, bustling your way through, and you see yourself. No matter, you know, if you're within range of this mirror, you see yourself. And you know, it's something going on around you, but mainly you see yourself. That is very intelligent artist, very physically intelligent artist. Okay, it's a wonderful piece of work. Okay, we got some other things to do here. I'll go ahead and let this one go ahead to that point. And I want to bring up Hamilton's, I think one of his most beautiful discoveries after he did the spinner, not spinners, but quaternions. After he did that, then he realized some other things that were coming out of his work there. And that's this. Two mirror planes. First mirror plane, second mirror plane. Okay? That means the first one acts first and the second one gets to act only after the first has. If that happens, then you get a rotation. We've already shown that. So here's the theta over 2 Darboux axis crank angle that we have in the third position of the three angles for a rotation so defined. There's the vector itself, which is the intersection of the mirrors, okay? And then the rotation angle is the magnitude of that. And we're actually creating here, due to these two normals, okay? You can think of imaginary normals coming out, and you're going to measure the angle between them, you see. That angle is this angle. That's the Hamilton turn arc, a theta over 2 arc, which will, when you look at the mirror, as we did with the clothing store mirror, and by the way, maybe you didn't catch the fact that in clothing store, they put that there so that you can look at your view from being right-handed, but also as you go like this, you rotate twice as fast, right? So with a really good one, you just go like that and you can almost see the backside, right? Okay? Now, they used to just have it for men, they didn't have it for women. But now the women's wear almost always has a mirror like that, because women are more careful about it. They care about what they look like coming from behind as well as in front. So anyway, that is thing. Now the other important point is that Hamilton's turn arc, you can slide it anywhere. I mean, it's always going to be theta over 2. You put it anywhere you want. Okay, now why would you want to do that? And that's the real rub here, is when we do two of these together. Okay? So I do a turn arc here, okay? And then I connect it to another arc made by another completely different crank vector that is not aligned with this one. If it's aligned, then it's a abelian combination. They get all the complicated formulas when they're not aligned, when there's a non-zero cross product between these two vectors. We got some work to do. But that work is really easy because all you have to do is the first rotation that you do comes to the intersection of those arcs, and the second one is comes off of that intersection point to give you the answer. That is, to give you the new rotation. Well, you have to realize that at this point, when you put those two together, the normal number 2 of this arc runs into the first normal of the second arc, and these two reflections cancel each other. They're out of here. All I'm left with is this point and this point. And it's only, all I have to do is draw a great circle arc to that point, and that is the answer for the product, and then perpendicular to that is the actual vector that is the answer for the rotation product of this first and that second. So that was Hamilton's intuition to how to handle in your head a three-dimensional rotation. Based on complex analysis, but I'm not doing any complex analysis now. I'm doing it almost exactly in my head. Well, not quite, because this is pretty hard to do, to find a great circle. Right? That's where this device comes in. Right here. This is the R3U2 slide rule, courtesy of the Earth Things Company, or Ear Things, depending on how you pronounce that. Okay? I would say it's the, it's total business failure, okay, when we did this. Total business failure. But it's probably the only device of its kind that has a majority of its customers Nobel Prize winners. Ramsey, Dudley Hirschbach, Dick Feynman.
What did Feynman use this for, Dr. Doctor?
He just bought because
Because it's good to play with.
cool. He just liked mechanical analog devices. That's how I got into Caltech. I told him I needed this thing to do differential equation, blah, 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 with a record player. He just, well, how do you do that? Right? Well, it's pretty easy, actually. It takes a lot of work, but the idea is very, very easy. This idea here is very easy, too, right?
So you designed that thing that you do?
Yeah, a friend of mine, Pete Gondola, got the production. You'll see all of the things that we've talked about in this course as far as polarization are listed here. We didn't talk about the optical matrix. That's an interesting thing. That's the way you actually propagate polarization. But you recognize the formulas there. But the main thing is, you see, I can do and I just sketched this up this morning. See those arcs on there? The way you get those arcs, for instance, the orange one, okay, is you just put this, I think this one was 150 degrees or so, something like that, 155 maybe. And then the other arc, this one right here, is located 150 degrees. So I have something that has an azimuth of 150. Okay, it's not quite lined up there, but using these crude markers, I put a Hamilton turn arc from there to there. And remember, all of the arcs on here are half the size that you actually rotate in real space. So this is the spinner at talking here with its 1/2, okay? And so all I have to do is find out where it intersects the other one that I want to do. I'm actually trying to turn that thing. I should go back here and turn it, okay? The other one's got as you can see here, a 20-degree polar angle, okay? It's pretty close to the equator, okay? And it is a rotation by 190 degrees. That's 190 degrees right there. 100, 110, 120, 100. So, because remember, a length on this thing gets you a lot further than what that is. That's, that angle right there is closer to 60, 70 or so degrees. Well, it's half of 190 is what it is, that one right there. So I want to rotate by that much, and here's the where they intersect. So I have 2 points that I have to worry about, right? The starting point for this arc right here, okay, that's the first one I'm going to do, and then there's their intersection, and the second one goes out to that point. So this is the initial point, that's the final point. How do I get the angles that go with that? Well, all you do is turn the slide rule until those two dots, the green and the orange, are located on the same smile line. And it's turning out to be pretty close to that 45-degree line. That would be the italic theta value would be just a little over 50 degrees here. And the angle that it would actually be turned, well, first of all, the azimuth would be 180 degrees. So you're taking care of those two angles. And then you just measure the distance along these lines here, because it would be along that line. You could actually draw that thing to that point, you see. So it's a pretty big angle. It's up there around 300 or so degrees, according to that scale there. Okay? And this is a stereographic projection. It's 1 over z. Right? That famous stereographic projection, 1 over z, that turns particle physicists into galactic astronomers, turns molecular physicists into planetary intergalactic astronomers, and etc. Okay? That means the intergalactic astronomers get converted at the same moment into atomic physicists. Okay.
So, Dr. Harter, but now do you have a program on your computer to
Good point. What do you think, TC?
We're halfway there.
What he has already is a 3D thing of that, but it's really hard to work that thing. This wouldn't be that hard because it's all right on a plane.
I have a slide for Hamilton terms. It's just not fully realized yet.
Yeah.
There's a placeholder for it in an app already.
Yeah. So,
Close.
want to work on it?
By all means.
Yeah. It's. I think it would be a neat thing, and you just use your, touch screen, right? I mean, this is just made for touch screens, right?
If I might, there's some new 3D technology called Babylon JS that fits in as a shim over what we've got that I recommend to everyone who wants to do 3D stuff online. Babylon JS. I'm migrating to it.
Okay, so this is the elementary product that we're talking about here. Now, it really shocks people to be told that just with vector addition, I can do that complicated thing called three-dimensional rotation. Whoa! And the first thing, if they're thinking, they come up with, hey, that can't be, that's absolutely impossible. Because rotations don't commute. And that's right, they don't commute. On a plane, when you add vector A to vector B, you get the same thing as you add B to A, right? No problem. No problem here, right? It really makes a difference whether I do this one first and that one second. That puts me up here. But if I do that one first and this one, remember they slide, right? Second, I'm down here with my answer. So we got to talk about that. This makes a parallelogram just like the vector addition would make, but this is a different rotation than that one. Okay, so that is a little sort of lesson about the products not commuting. Okay. Now, as this shows, and I'll go ahead here, each arc, okay, and I hope I have that on both of these. Each arc, theta over 2, phi over 2, or this guy here. Again, the actual arc, that's the size of the arc. It's a half of the angle that is actually being accomplished by the rotation that you're imagining in 3 dimensions. So each of these is half of the actual angle of rotation that you're worrying about. So I want you to, first of all, remember very much that that's true, okay? And therefore, the supplement, plus and minus 2 pi, that just comes out to plus and minus pi. So an arc that goes 2 pi only makes it halfway around on this sphere. So this thing were to go halfway around to say about there, inside, on the other side, okay, this would correspond to a plus, and that would be a minus. You would be at minus 2 pi. This would be 0, which is the same as plus 2 pi in our world, right? But in spinor world, you're as far away as you can get. You're on the other side of the world, right? So that's why the title of this paper that we wrote about this, Dos Santos and I, is called Double Group Theory on the Half Shell. And we're talking about a half of a shell on this device. Okay, and then we're doing what's called double group theory, which is a group theory where you put in the minus signs for all your products, as though we were going to deal, and we'll show some pictures of that very shortly. So the real point here is that for quantum spin a half object, arc pointing from n1 to minus n2, okay, represents a phi rotation with an extra pi phase factor. That is, it's the minus the rotation. Okay? So it's really the same rotation on the two sides of this thing. It's just that one of them really should have a minus sign if you're working with those weird things called fermions that constitutes 99.9999% of every one of our bodies, right? There are very few bosons in there. So that's a worthwhile thing. So this guy right here is the same rotation as that guy for three-dimensional values. Or it's minus the other one, and you have to decide which side you want to have the minus on. That's up for grabs. Okay, so let's talk a little bit about that. This is the device that we've been playing with here, and here is it at work turning crank angle into Euler angle in just a couple of moves. I won't go through that right now. There's a picture of it on the scanner. That's what the scanner does with the slide rule. Pretty funny. Okay, and then I was thinking I could actually put that on top of it, but it doesn't work very well. Okay. So this is where the geometry meets an analog device. And that, I think, is cool. Definitely something to try for. Okay, it doesn't show as well over there. And there's another device that they're sitting around here. This is Sundial. Works off the polar angle. It's really precise. Tells you when all sorts of things happen. Like I started to get a lot of skiing cancers from doing a lot of skiing, swimming, tennis playing, and all kinds of stuff in the sun. So I wanted to know where was the erythemial threshold point at a given time or location in the world. So this is what I built in Brazil. The other reason I built in Brazil is because the power goes off all the time. But the sun's always there. There you go, right? So, but Brazilians don't care whether they're late or not. So I was always on time to an empty room. Okay, so finite group products here are the other thing that we get with this. And so I wanted to show you that just to give you, we want to eventually be able to do finite group products efficiently. This is one way to do it, and it's the only way I know of if you're spin a half, but if you're not spin a half, there's some easier ways to do it. In any case, we're going to have a group table for trigonal motions. We're going to have a group table we need in order to study what the angular momentum does on sulfur hexafluoride or on a buckyball when you're in the neighborhood of a trigonal axis. That is, the 1-1-1 direction is a trigonal axis for the octahedron. And there's lots of trigonal axes on this thing. Every one of those things that looks like a hexagon but isn't quite is a trigonal axis. So we're going to be playing with representations of a group that has this multiplication table. And most of the time we won't care about the minus signs. But if you do care about the minus signs, you just do a stereographic projection, namely this slide rule of the Hamilton turns on a sphere, and there are all of the 180-degree rotations. There are only three of them, row 1, row 2, and row 3. But then there's minus row 1, minus row 3, and minus row 2. Remember, the two together, if they went in the same direction, would go 4 pi. One of them stopping at a minus and the other ending up on plus. So if you use this device here, you will be getting the correct plus and minus signs for a spin a half object, and you will put the minus signs in the right place on that table. And this particular result here is that row 1 times r, this is row 1 right here, and r1 is 2, and it looks like this is one I picked this where the sign is contra. This is a sign developed one way. The other way is to change all the pluses and minuses, and that's the one that I should have put there because that's what this thing is giving us. And when we put the row 1 first here, and then the R second, then you get a minus row 2. Okay, now, much easier. If you can ignore the plus and minus signs, which we mostly will, all of the molecules that I can think of are integral spin. So this works a lot better. Here you do what I call, well, I just call it a chart of the group. But basically what you do is you put your axes down here in black and show you know, where the rotation hardware is. And then you imagine wave functions named by the rotations on the you know, on the body that has the symmetry. So for example, starting from 1 here, you call that one the origin, and then I apply a 180-degree rotation row 1, I'll flip it over to here. So I put row 1 down as the name of that particular locality. So these things are like the Euler angles. They're coordinating the wave function. These things are like the axis angles. They sit in one place and do their work on the wave functions that live and move around different places. So you can see that the rotation r squared, or the rotation r, this is r to the first power, that's the same as r squared. Forget the plus and minus sign, it would be minus r squared on the correct chart there for fermions. Forget this plus and minus sign. There, right there, is the effect of r squared, which is this right here. It takes 1 over to there. Flip, there it is, you see. So you get all the possible products very easily just from doing that. And I point this out as a neat idea. And that, for example, you say, okay, suppose I have a state R1, it's there, and I do a row 1 on it, okay? I do a row 1, that's a flip around that axis by 180 degrees, and I start from there and go to there. That's the answer to the actual product. That makes it really easy to get these products just by looking at that thing. You don't have to write anything down. You just look at it. Okay? Now this one you can do that too. You're really skilled to get the minus signs, but this one ignores the plus and minus signs. So the chart is, you know, much faster, easier. Pray that you're dealing with bosons because you're going to have to do this if you've got fermions. This is called a double group. It's called a double group because they take the minuses as a new element. So they have a whole bunch of elements here. They make this thing that's a 6 by 6 into a 12 by 12 just to do D3. And then they struggle to get all the representation. They throw away half of them. Okay, so this is really a waste of time, the double group thing. This is an algebra. We're doing everything algebraically, so we don't have to play that game. We don't have to do the full group at this. This is what the octahedral guy looks like. Okay, all 48 elements, 24 elements if you just do O symmetry, which is half of this thing. Every one of the ones up here gets multiplied by an inversion and is corresponding place down in the lower half. Okay? And then there are various things that have this symmetry. It's something that has the T symmetry, it's something that has TH. That's really amazing symmetry because that's the doorway to the icosahedral symmetry. We'll be discussing this later on. Then there's the Tetrahedral Td Symmetry, which is the symmetry of diamond. Buckyball, Buckminster fullerene, has a TH symmetry in its crystal. That's one form of carbon. The other form of carbon that everyone knows about, the diamonds are forever. is Td symmetry right there. But all of them can be analyzed by this little cube here. Same thing. You have the operations, they don't move. You imagine that these things do move from the identity, which is right here. So again, you can just look at that and make any one of the 24 times 24, actually 48 times 48 products quickly, easily, if you get good at it. It's a little harder than D3. So there's the actual nomogram that would give the thing with the correct signs. That's this thing. So there's the full octahedral table with the correct signs. It's in the textbook, and that's the thing it would give it right there. Okay, so we're doing pretty well today. We're going to finish early, I think. Any questions about this? We've got a couple more things to do here that I think you ought to see just to start getting used to them. Not the least of which is the Buckyball Symmetry. It's almost too much to take. These are all of the symmetry operations of C60. Okay? We're talking about literally 60 operations.
Dr. Harter, how did you generate that group table? Like, did you work it out by hand, or did you have a program that enables you to figure out
In the computer age, I would have never done it. But yes, the first time I did it, I wrote the whole damn thing out.
Ah, okay. But
I was giving lectures at NASA, and I figured, well, geez, they're paying me to do this stuff that I really love to do. Even when I come up with something like this, I better do it. I made a lot of mistakes, but it obviously better do it with a computer, right? Even all this apart. And the same thing is really true for this. This of course is a 24 by 24 table, and the rest of it is 48 by 48, but the only difference is all these numbers go through onto the other table, and the one down there, and then the one back there, the numbers reverse. So you get, you can make this work for spin and half as well. But more important to label the axes with the group operators and that sort of thing. That's more difficult here. And this time I'm labeling them with the permutations of 1 through 5. You see, each of the numbers shows part of, you can see a part of a TH structure. The 4 is here, there's another 4 right there, there's another 4 sitting right there, and there's one sitting down there, okay? And then the 5, it's similarly displaced according to another orientation. But the idea is that each rotation, just the rotations, not the full reflections symmetry group of IH, just plain I, or Y actually is the letter used to describe this group. Each one corresponds to an even permutation of 1 through 5. So you'll see here, for example, that's any cycle that has an odd number of numbers, it's an even permutation. There's 3, okay? There's another one that's made out of 5. Okay, so those two are kind of partners. We're talking about 44 degree rotation. This is twice the 72 degree rotations. But the 120 degree rotations around threefold axes, okay, they're all done with tricycles. And then finally, there's the 15 rotations that are 180 degrees, okay, and you end up with 2 bicycles describing it. So that's half of the permutation group, 5 factorial. 5 factorial is 120. Half of that group is this thing, C60's rotation. So
this is what we're dealing with when we talk to this fellow, Mr. Buckyball here, Mr. Buckminster Fullerene. And it's hairy. Now, TC has programmed all of the modes for this, and we're going to be re-looking at that in such a way as to make better force constants, so that we'll be better at predicting whatever spectra comes when someday we do actually get spectra of this molecule. Now, this is what it looks like on one of the U2 diagrams, and I have been unable to really use that. We've got to do this with silicon. But just to get an idea of what it is you'd have to do if we didn't have the silicon, right? You'd be stuck with something like that. Okay, now equivalence classes. We might as well do that now that we've got the products available to us. And then I do want to really quickly go through the whole nother way to view the two-state system using density matrices, density operators. So we've got enough time, I think, to do that easily. And I will not belabor this one. I just want you to see it so that you can make comments about what we might do if we have a 3-level system or a 4-level system. Okay, unitary 3, unitary 4. And that's what we're going to begin discussing next time, is how to use quantum oscillators to make representations that go with first U2. Okay. Here is an example of an equivalence transformation. Equivalence transformation being one that operates fore and aft, so to speak. So I'm going to do a rotation, R1, okay? In other words, I'm going to just say I want to take this axis, row 3, and transform it with r to the first power. That's a 120-degree rotation. I want to see what happens if I do a 120-degree rotation of this thing in the diagram like this, which is part of the group diagram that ignores the plus and minus signs, right? Well, you can see just, well, it's really obvious. I simply get row 1, okay? That's so obvious, right? But that is an equivalence transformation. It's not just the product of R1 and row 3, okay? It happens, the product of R1 on row 3 is row 2, but that's kind of well, we'll discuss it in a minute. But you see, you could have gone the other way. I could do row 1, row 3, I wouldn't get the same answer. This is something that you very easily visualize, and this is what you're actually doing. So the idea is I'm really making a transformation R1 on the kets, and then the bras get to operate with a transformation. It's a conjugate with all of this stuff. They're unitary operators. So this one is the inverse, or the R1 dagger. Okay, what unitary means is that should give you the inverse. But that is what you doctor orders for operating on the bras being the things that point this way. So the operator comes and hits on the flat side. Now, the inverse of R1 happens to be R2. Okay, this is R1. R squared goes to here, but if you don't care about the plus and minus sign, that's R2 right there, as you can see on this chart. Well, to use the group multiplication table as it is, we discovered that row 3 transformed that way is row 2 r squared, okay, and that turns out to be row 1. Okay. So just multiplying them doesn't give the right answer. You're doing this And that is the right answer. Row 3 is turned into row 1. So that's an equivalence operation. They're much easier to do. The equivalence operation, as I've already said, for rotations. Just move the crank with a rotation. That's what we did here.
That looks like when we used to do like permutation tables in abstract algebra. But you use
These are all,
swap.
just like this thing's isomorphic to permutations. I should say semi-isomorphic because it doesn't get the whole S5. It only gets A5, alternating 5. Okay. This is tricycle, tricycle, bicycle, bicycle, bicycle. S3. 3 factorial is 6. So it is exactly the permutation group. No halfway thing like this one. And the octahedral one is 24. That's 4 factorial. It maps straight away to the 4 factorial permutations. So all of these symmetries that we've got arrayed here are permutation groups that we know and love, right?
Yeah, I was reading a book about it, but the math formalism behind it. And
Yeah.
I think those are like the most useful groups when it comes to.
Well, the permutation combinatorics is the prince of combinatorics for physics. The most powerful language is the language of the tableaus of the permutation symmetry. You calculate incredible stuff with that. And it's just child's play. It's really the most powerful mathematics I know. It makes Dirac notation even look primitive. It's really incredible. We'll do some of it, okay? Here's another one where I took P3, got row 2. Yeah, it's easy to see. Now, this right here is something maybe not terribly important at this point, but remember when I said that if you went backwards, in other words, if I do this operation right here, which is a blue theta, and then after I've done that, I then do this operation, that comes next, and you got to remember to keep them in the right order. I get a very different thing. That's this thing right here. This guy right here is the result of doing the the blue theta first, and the green theta, this vector crank, second, is this guy that's called the red theta double prime. All right. If I reverse that and do this one first, that's second. I got to bring it down here, and then I got to bring this one over here. You see? So this one's first now. Okay. That's this guy right here. The green theta prime is first, and then I do the second one. Okay. That's this guy right here. Is that clear? I get a very different thing. I get this guy. So in a sense, it's like adding translation vectors on a plane. You get a parallelogram, but this is very different from that. This is very different from that. And so this is just an exploration of the things that you get by applying operators in different order, or operators involve an inverse in different order. And the third case, of course, is an inverse involving the green guy in different orders. I didn't go that far. Now, the one that you'll find in that group theory textbook is this picture. Same thing, a parallelogram, except now it's very clearly showing that this R right here is equivalent to this one. That is the T operation, which is, this is the T operation, this is the T inverse operation right here that go along the diagonals. And then these are operations right here that are what we call cosets of the subgroup of T operation. A coset is that group multiplied by the element. So I have this one right here, and if that wasn't inverse, I can have it going backwards. But in any case, the idea is that this operation right here is equivalent to this one. It's just TRT inverse. So the next few slides on this exploration are just of equivalences. And so I'm going to bring this one up to speed just to make that point. But here's an equivalence, you see, and minus means inverse. Okay, so that particular product right there with the inverse is the green one, and then the reversed product is the also the green one when you undo some of these things. So there are two ways to look at the parallelogram: is these are equivalent, or find a way to make this one equivalent to that one. What's going on here in the rotation group is that whenever I do this guy right here has to have the same angle of rotation as this guy. And that's an old thing from spherical trigonometry, the kind of trigonometry that the navigators used as they explored the new world, quote unquote. Okay. There are all sorts of beautiful sort of spherical trigonometric results that the group theory is giving you essentially for free. You just play around with the operations, doing different things to them. And that's what this is, and it's better that you study it on your own to see the very simple relations that are occurring here with that. Okay, now this is something we certainly got enough time. If you want to spend some time with this, you're welcome to it. But I'm going to go rather quickly through this because this is just another approach. This is the density operator. Density operator is what you get when you take the stuff that we've been working with, the kets that we've been working with, and just outer product them with the corresponding bras that you get by conjugation. So you end up with what's called the row operator. And the expectation values of these various operators we've already looked at. Of course, that's the probability that exists, and that's the four-dimensional norm that these things would obey if I set the quantum number that we're going to use later on for this to 1. So this is a 4D norm we're talking about here. And this is just that what we called the A expectation value, the asymmetry we called it, the quadratic function of the phase variables, again scaled by half. So this is stuff we all have dealt with so far. There's the X and the Y expectation values that we've already seen. Here's other ways to write them. The real and imaginary part of what's called the coherence in two-state language, the psi star 1 times psi 2. Okay, there's a real and imaginary part of that complex quantity, and it is the X and the Y components in polar coordinates using Euler angles. So this is all stuff we've been through, but I just wanted you to see that because the density matrix stuff is not that different. But in any case, the idea is, well, shouldn't the state be an operator? This kind of way we've been playing it, the state is described by Euler angles, these alpha, betas, and gammas. It has a coordination, the x1, p1, and x2, p2, and the polar angles that go with it. This is kind of a weird 2 plus 2 equal 4 coordination, whereas the coordination of the operators is 3 plus 1 equal 4. That's something that's powerful about the method we've been using, and it's not brought up at all in the density operator description. Nevertheless, that's the way the density matrix looks like. It's got a plus SC here, and it's got a minus SC there. And then it's got the 1/2 n, which is the unit operator that just wiggles the overall phase. But the actual Hamiltonian is just sitting essentially in that form right there. These 4 components right here. Those are the density matrix components for a two-state system, written out in a way that kind of makes sense. If you put the star on the right, then you get 1, 1, 1, 2, 2, 1, 2, 2. But if you do it the way you normally do it in quantum mechanics, put the star in the middle, it flips. But this outer product is what we're working with. That is the definition of the pure state density operator. And the power of the density operator is that if you have statistical, that is classical statistical probabilities that are messing you up a little bit, you can put it right in to the density operator. And boy, do we ever have that in information science, right? That's the main things, the noise and stuff that's killing our beautiful phase. We got to include it. We've got to calculate. That's what your dissertation is going to be. Everything works out about that way, essentially. So this is neat. Now you take the density operator we just got and expand it. What do you get? Spin vector components. So that's what we were working with. That's our thing that's being swung around, right? The Hamiltonian still is nowhere in sight.
So, Dr. Harter, one thing, n is your norm, norm of the vector,
Yeah, that's this is where I use the actual spinners, but then the S's are the angular momentum that will come out with quantum number half. Okay, so that's it right there. That's the way to state it. Okay, so the density operator has a sigma expansion that we already recognize for our Hamiltonian, right? But we're going to be describing a state with this, you see? So they come out to be the same, essentially. It's just that we usually use the sigma straight away and have the frequencies be little omega A, little omegas B and C, because we like to work with things that are slow. Okay. Another way to write it, okay, SA, SB, SC. This is the Hamiltonian now. Okay, so this sums up density operator for us, and it's pretty much the same as we do more complicated things in spin vectors. But that's something we'll tackle a little bit later on. But here's the Hamiltonian, and it's got an omega crank right here, dot sigma. Here's the density operator that describes the state. It's got an S vector, Stokes vector, dot sigma. And it's just a commutation of those two operators that gives you dynamics. End of density matrix theory. Okay? Here's the deal. Okay? When you take the partial derivative of a density operator, you got to do both the bras and the kets, right? There's the equation that works for the bras. It's got a minus sign here that this one doesn't have, because you dagger this to get that, right? So the daggered bra equation is time reversed. These guys are living with time going backwards. These other guys are living with time going forward. Can we make some hay about that? I think we can, but it's just people are reluctant to do that. In any case, here's the actual partial derivative of this product. It's this one with the derivative plus this one with the time derivative. So it's this combination right here, and that's this. So there's the beginning of the master equation. Okay, still no probabilistic stuff that added to this to make for the damping and the noise and the you name it, right? But that's the start of it, right? So then what we've got to do is work these two guys out and subtract it. Okay. What happens is pretty much those things just disappear. The scalar parts disappear. So the commutator is very efficient in that sense. Okay. And basically what we have is the expression here. These guys cancel. This remains because the cross product is different when A is crossed B than B is crossed A. There's a difference in sign mainly for that. So that's what happens right there. That's what's going on right there. This boils down to cross S. This one cross S cross omega is very different in terms of sign from omega cross S. Okay, so you just get a factor of 2 multiplying a half, which gives you 1. There's your result right there. sigma dot sigma with an IH, cancel the IH off, throw away the sigma, and what do you got? Swing the spin vector around. That's it. That's what the density, if there's no noise, right? There it is. Okay, so that's what we were doing. That's what we're doing with this device right here.